When modeling for construction, as opposed to modeling to illustrate design alternatives, it's important to place your building elements in a way that accurately reflects the construction methods and techniques that will be used. Each construction material, for example steel, concrete, and wood, has its own unique construction techniques and joining methods. So we must take extra care when creating our building model to accurately reflect these. Let's take a look at a model of a simple building carried out in those three different construction materials and look at the critical differences. Let's start with the steel frame building at the top. We'll zoom in to take a closer look at the construction, and you'll see that this building is modeled in a very typical way when creating models that will only be used for design. The steel columns are running from floor level to floor level. The floor decks are placed at the floor level, and the beams and beam systems are also placed at that floor level. Now, this approach to placing the elements doesn't make a difference for visualization, but for structural analysis and construction modeling, several aspects of how those elements are placed should be adjusted. For example, in a steel frame building, the columns typically don't run from floor level to floor level. To facilitate easy joining of the column elements in the field, the tops of the columns will actually be offset above the floor level, say 3 feet, where it'll be easy to join them. To compensate for that, the columns on the second floor level should have an equivalent base offset. So again, entering 3 feet to put the join in the proper place. We should repeat this for all the column elements. The structural floor slabs are located at the correct elevation, but the beams and beam systems are actually protruding up through the floor slabs because they're located too high. Rather than placing beams and beam systems right at the floor level, we should take the thickness of the structural floor into account and lower the elevations of those beams and the beam systems. Let's look at how that's done. Let's hide these floors to make it easier to see the beams and beam systems. We'll select one floor, then Control-click to select the other, then right-click to hide them. Let's select one of the beams so we can explore it further. If we select this beam at the front of the building, you'll see that it's been placed spanning from one end of the building all the way to the other and isn't breaking at the intermediate column. Now this isn't accurate. The beam would actually be placed spanning from column to column, so this inaccuracy will create problems when doing the structural analysis and when simulating the construction process. So let's change that. We'll delete this beam, then place new ones, switching to the Structure tab, choosing the Beam tool, then selecting the appropriate beam type from the Type selector. We'll choose that wide flange, W12 by 26. We'll change to the appropriate reference level, level 3. And we'll also change the Z direction justification. Rather than placing the beam at the top, let's place it other and actually lower it 5 inches to account for the thickness of the structural floor. We'll say Apply. Make sure that 3D snapping is turned on. Then place the new beam elements by snapping to the ends of the columns. And when the beam elements are placed, you'll see that they're actually placed 5 inches below the floor level. We can change the height of the existing beams too. To do that, let's select one, then Control-click to select the others, then choose the Z direction justification again, choosing Other, and let's make that also -5 inches. And Apply to lower those beams too. The beam systems share a similar problem. They're also located too high. We can select the beam system by hovering over one of the beams, then tabbing until we select the system. We can then enter the new elevation, again lowering it 5 inches to account for the thickness of the floor slab. We should make these changes to all the beams and the beam systems in our steel frame. And when we do, you'll see that a section view cutting through the steel frame now represents those connections accurately. Let's zoom on in and take a look at the connection of the steel members. If I switch this view to thin lines, you'll see that the steel beams now line up perfectly with the bottom of the floor deck. Let's look at how these same principles apply to the concrete structure. From a construction modeling perspective, concrete tends to be easier to work with, because beams and concrete slabs can both be placed right at the floor level. As a monolithic material, these two types of elements will merge together just as they will when the concrete is placed. We still need to consider the accuracy of our beam spans. Let's take a look at how they're modeled. Again, we'll hide the floor elements so we can see the beams more clearly. Selecting one floor, selecting another floor, then right-clicking to hide those elements. The concrete columns look a little odd right now. They're actually spanning from floor to floor, but because I've hidden that floor element which is merging with the columns, it looks like a piece is missing. Don't worry about that. They actually are modeled accurately, and when we unhide the floor elements, everything will be fine. Let's select one of the concrete beams. You'll see that we have a bit of a problem here. Like the steel structure, rather than modeling a single beam that spans the entire length of the building, it's probably better to model those as separate beam elements. To do that, we'll use a similar procedure, deleting the existing beam, choosing the beam tool, selecting the appropriate type of beam in the type selector. We'll use the concrete 16 by 32. The placement plane will now be level 2 for these beams. It'll be a top offset. We don't need to offset it below the floor since it'll merge into the floor, and making sure that 3D snapping is turned on. With all these set up, we can now move into the model area and snap from endpoint to endpoint of the columns, placing the new beam. Let's pan a bit, and we'll do the same for the rear beam, spanning from column to column top. We should repeat this for any other beams which span across multiple columns. Let's take a look at the section view of the concrete building to see how those elements merge together. If we open the section view and zoom in just a bit, you can see that Revit very smartly handles the merging between the beam elements and the floor elements. Since these elements are made of a single material, cast-in-place concrete, Revit will automatically join the elements as they will be in real life. Let's turn our attention now to the wood frame building. We'll switch back to the 3D view and pan that building into view. In many ways, the issues we encounter when modeling wood frame buildings parallel the ones we encounter when modeling steel frame buildings. As stick-built systems, as opposed to poured-in-place systems, it's important to take the interferences between the various types of framing elements into account. So, like the steel frame building, we'll need to look at the beam spans. Again, we have the problem here with a beam spanning across multiple columns. You'd fix that in the same way we did for the steel frame building by deleting the existing beam and placing two new beams at the appropriate elevation. In determining the appropriate elevation for our beams and beam systems, we need to consider the thickness of our subfloor assembly. Let me switch over to the section view for the wood frame building and illustrate what I mean. If I zoom in the middle of the floor and change to the thin line view, you'll see that the plywood web joist elements that we're using in our beam system is interfering with the wooden subfloor. We can select the floor element, open its type properties, and explore the structure to see what the thickness of the subfloor is, in this case 3/4 of an inch. Close that, and then change the elevation of that beam system to lower it 3/4 of an inch, so those plywood joists no longer interfere with the subfloor. So those plywood joists no longer interfere with the subfloor. After making that change, you'll see that we now have an accurate model of the interaction between those joists and the subfloor. Another consideration to keep in mind when modeling wood frame structures is the interaction between the wall framing elements, often called the studs, and the posts, beams, and other framing elements. Let's pan on over to the wall assembly and take a look at how walls should be aligned. This wall was placed with the center line of the wall lining up with the center line of the beam, and while that made for convenient modeling, it's not accurate for how the structure will be built. The outside face of the core of a wood frame wall is typically aligned with the outside face of the structural framing elements. That way, the sheathing material applied to the outside of the framing elements will have a smooth surface to be applied to without any interruptions. To model that accurately in Revit, we can use the Alignment tool. Let's switch to the Modify tab and choose the Alignment tool, then select the outside face of the framing elements and select the outside face of the wall's core to be aligned to that. When they're in place, you might want to lock them so the wall doesn't accidentally get shifted from its proper location. Let's return to the 3D view and look at one more important construction modeling issue. When placing walls on our structural frame, we should also be careful to model them in a way that accurately reflects the way they will be constructed in the field. For example, this wall is currently modeled as running the full height from level 1 all the way up through level 3. While that may be appropriate for balloon framing or some curtain wall systems, it's not typical for most wood frame buildings, which use platform framing with walls that span a single floor level supporting the next floor platform. To properly model this floor-to-floor framing technique, what we should do is adjust the top and base constraints of the wall to model the individual wall elements. Let's go to the Properties palette, and we'll change the top constraint of this wall. Instead of going up to level 3, we'll choose level 2 and say Apply. Then to quickly create another wall to span the next floor level, what we can do is copy this wall and paste it aligned to the next floor level. If we place it on level 3 and say OK, you'll see that a duplicate copy of the wall is placed above the first one, but as a separate element, which is a more accurate representation of the true construction condition. You can download and install an extension to Revit that's especially helpful for modeling the framing elements in a wood frame wall. Let's switch to the Extensions tab, and we'll take a look at it. It's under the Modeling pull-down, and it's called the Wood Framing Wall extension. To illustrate how to use it, let me add a simple wall to our model, and then we'll use the extension to quickly model the wall framing elements. I'll return to the Home tab and choose the Wall tool, then place a new wood frame wall using the edge of our slab here as the exterior face of the core. Let's pick that edge, and our new wall is placed. Let's select that wall, then return to the Extensions tab and select the Wood Framing Walls extension. We can set properties for the wood framing that we'd like to have automatically generated. For example, for the current wall, within a 4-foot span, we'd like to have either 1 or 2 intermediate studs. One intermediate stud, we'll place them at 24-inch centers. 2 intermediate studs, we'll place them at 16-inch centers. The profile for the stud elements is currently set to be 2 by 4. We'll change that to be a more accurate size for 2 by 6 walls. We'll set them to be 5.5 inches by 1.5 inch. We can choose the framing style to apply at the boundaries and the openings in the wall. For example, we can choose the corner framing, the top plate, and the bottom plate. For the top plate, let's choose a double top plate. The bottom plate we'll leave set to a single plate. For the openings, we can set how we want to handle the king studs and trimmers at the sides of the openings, as well as determining what we'd like to appear as a header and for the sill of those openings. Currently, these options are unavailable because we haven't specified any openings in that wall. Let's say OK to create some simple wall framing. Click the OK button. The extension goes to work. And when we return to the Revit window, you can see that we've added studs to those walls. They're currently spanning 2 floors, so we'll want to make some adjustments to that wall, as well as adding a few openings to it. Let's change that wall height so it only spans a single floor. We'll change the top constraint to level 2, say apply, and the wall moves down. The framing elements haven't changed yet. We'll need to rerun the extension to have them update. Let's try adding a few openings to our wall. We'll switch to the Home tab, choose some windows, and place some windows on that wall. As well as a door or two. We'll select the wall again, return to the extensions, and reopen the wood framing walls extension. When we click OK this time, the extension goes to work and recomputes the framing in that wall. You'll see that the extension has adjusted the height of all the framing elements and made allowances for the window and door openings. There are still a few missing pieces above and below the window openings, so we should return to the wood framing extension, adjust the settings, and specify how we'd like to handle the framing in those conditions. The wood framing walls extension illustrates the power of using parametric modeling. As we continue to adapt and make changes to our model, the parameters that describe our building elements can in turn automatically drive and regenerate the related elements.